All right, so today we're going to be talking about torque. So your first question, well, what is torque? Really, that's the force that's going to uh, make something move in kind of a circular path. It's a force being exerted on an object that can only move in a circular way. Um, it's different from, say, centripetal force, which is the force applied to an object that accelerates it towards the middle of a curved path. This is just kind of slightly different from that. The best way to think about torque is using a wrench. So, like if I have just kind of a bolt there, my wrench kind of fits in something like this. Uh, Stop it there. Really, what the torch is, thank you, Flipboard. You know, so I've got my wrench here. It's the force I apply to the wrench in order to get that bolt to move. Okay, so let's go ahead and get rid of that. All right, so the equation for torque, first off, the unit for torque is really newtons per meter. We're going to find that torque is based on how much force is being applied, how far away from that center of rotation that force is being applied, then also um, what degree from the radial is that force being applied at? So to kind of explain that part, so the equation is right there. To explain the angle part, if I'm looking at kind of these three things here, we'll pretend like this is something moving, kind of this radial path here. I'm applying a force straight up, according to this diagram. What the radial is if I kind of take whatever that object is and then I kind of extend it out, it's the angle from that. So like that would be a 90-degree angle. Even on the other side, the degree from the radial is a 90-degree angle as well. And here, if I extend this out, let's say that's 20 degrees. In this case, this middle case here, since it's the force is being applied in the same direction as the radial, we're going to say that's kind of 0 degrees. And here, once again, extend that out. Let's say that's 30 degrees. Okay. Really, it's kind of if you extend it out, what's the angle that force is being exerted at? So to just kind of use that. So two scenarios here. Uh, Let me fix this stuff quick. Okay, two scenarios. Both of them involve opening a door, opening the same door using the same amount of force. I'm going to apply 3 newtons of force to this doorknob. At first, the door is closed and I'm pulling directly away from it. So if I kind of, extend it out the radial, I'm pulling at 90 degrees to the radial. So let's go with number 1. So really, I want to know how much torque is being applied or is the door experiencing. Um, the doorknob in this case is 0.8 meters away from the hinge or from that center of rotation. So in this case, the torque, which is that funny looking T thing, it's another Greek letter we're working with. That torque is equal to the radius. In this case, that's 0.8 meters. And that'll be times the force. We said that the force was 3 newtons. This is a nice steady 3 newtons. And we're going to take that times the sine. Once again, the angle, sorry, up here, the angle from the radial. So if the radial is kind of straight out that way, I was applying it perpendicular to it, so 90 degrees. So the sine of 90. So now I just need to get out my calculator and hope that it's going to load all right. All right, so we're good there. All right, so the way my calculator works, I have to do the sine part first. So I'm going to go 90, hit the sine button. Okay, so that's 1. That's not going to change anything. And that makes sense, that 100% of this force is in the direction that doorknob's going to be moving in starting off with. Okay, so 1 times 0.8 times that radius times 3, 2.4. All right, so the torque in scenario 1 is 2.4 newtons per meter. Okay, and we're going to come back and look at that a little bit here. So then let's look at situation number 2. All right, so the door's opened, quite a bit now. I'm still applying that 3 newtons of force, but now if I'm still applying that 3 newtons straight out, Like I'm not applying it in the direction the door is moving. I'm just pulling straight towards me. Now my angle from the radial is 60 degrees, okay? So I'm looking for torque again. That doorknob still hasn't changed. It's 0.8 meters, okay? 3 newtons. Now in this case, I'm taking the sine of 60. All right, so let's bring this back up. So I've got 60 sine. Okay, so now it makes more sense. So now what the sine of 60 tells me is, some of that force isn't being applied in the direction that that door is moving. It's now kind of being applied, you know, essentially in this kind of worthless direction straight out. Okay, and essentially what we're going to see is, if I bring the calculator back up, is roughly 87% of the force being applied to actually get the door to open up. Okay, so I'm going to take that times that force of 3 newtons times that radius from the hinge, zero point 0.8. And this time I got 2.08. We'll just call that 2.1 Newton meters. Okay. So in this case, that torque changes as that angle changes. Okay. So the angle decreased, we got less torque out of it. All right. So third scenario time. Let me go ahead and erase this stuff down here. Okay, so now that we kind of understand radials. So let's go back and look at scenario 2. I'm going to call this 2-1, okay? So we still have, so that's my door frame, got a hinge connected to a wall. We're still going to do this. Okay, this time, let's say our doorknob's quite a bit closer to the hinge. We're still going to pull straight out with 3 newtons of force, but now in this case, and you know what, we're even going to say that we're going to use that same angle of 60 degrees. But now let's say that that doorknob is only 0.1 meters away from the hinge, okay? So 2 prime, 1 I should say. So now my torque, I'm still going to use the same formula. That radius though has changed to 0.1 meters. The force stayed the same at 3 newtons. And we're using the same angle as we did for the last part, okay? We just moved the doorknob closer. So now, if my radius isn't nearly as big, I've got 60 sine times 3 times 0.1. All right, so now I end up with 0.26. Actually, I'll probably just leave it there. All right, so 0.26. And that's Newton meters, okay? Really what we're finding here is, and this is something, pretty basic and intuitive, is it's easier to open the door with the doorknob on the outside. If the doorknob is closer to a hinge, I have to apply a lot more force to it in order to get that same torque out of it. Um, that's something we're going to look at a little bit in class with kind of a lab activity. Uh, but for the most part, I just, looking at the equation even, even if we ignore real life and we just kind of look at the equation, I know that the more force I apply, the more torque I'm going to get out of it. The farther from the center of rotation I exert that force on, the farther I'm going to get. And once again, I want my sine, the best angle, the angle that gets me the maximum torque is going to be 9 degrees. At that point, that's equals 1, and all of my force is going into that torque. All that force becomes torque. And keep in mind, using these trig functions, you can't get a value greater than 1. It just tells us, what percentage of our force is in that direction. I hope that helps out a bit, especially with that radial kind of explanation. I think that's the toughest part for this. The other thing to keep in mind is with all of our circular motion stuff, we made sure our calculator said radians. We were looking at the circular motion. Now we're kind of going back. We're looking at, what I will call translational force and stuff like that. Like our force isn't actually moving in a circle. It's not changing the angle. I mean, it is, but the force is more kind of in that kind of 2D square kind of reference frame that that works with. So with that confusing little rant there at the end, good luck with practice.